Hey folks, this is Miss Nichols, and this first lecture in our magnetism unit is on basically what is a magnet. So let's start by reviewing what we already probably know about magnets just from playing with them enough in our lives. The first is that two permanent magnets will attract or repel each other depending on orientation. So if you take two magnets from your refrigerator, you will notice that sometimes you can make them pull together and sometimes they will repel. The two sides of the magnets are called the North Pole and the South Pole, instead of positive and negative like we have with circuits or with charges. And I do want you to just ask yourself, have you ever seen a magnet without a South Pole or without a North Pole, a one-sided magnet? We're going to come back to that later on, whether that exists or not. Opposite sides of the magnet are going to attract each other, so a North Pole will attract a South Pole of a different magnet. And like poles are going to repel each other. So North Pole repels North and South Pole repels South. That's the same as it was with electrostatics. There is no force between just two random objects in the world that are not these kinds of magnets. So a balloon and a paperclip, for example, are not going to be attracting to each other. Or two pens don't have any magnetic force of attraction. So most objects don't experience this magnetic force. However, if you have one magnet, sometimes that does attract non-magnets and sometimes it does not. So that magnet does not attract this balloon, but it does attract this paperclip. You probably, through playing with things, realize that the things that are sometimes attracted are, generally speaking, iron-based materials, metallic iron-based materials, but not all metals, and we'll get around to that later on. And obviously, if you stick more magnets together, they become stronger and they can pick up more paper clips. So before we get into what really a magnet is, I want to go back in time a little bit and talk about what we've used magnets for in the past. The original magnets were just naturally occurring rocks, known as lodestones or magnetite. And magnetite is a magnetic mineral that becomes a magnet based on Earth's magnetic field, basically creates a magnet out of a molten material. And we'll talk about how and why later on. But when the first people discovered these magic lodestones, magnetite, it really revolutionized navigation because they were able to create something called a compass out of this lodestone. A compass is basically a very tiny needle on a very low friction surface that can turn and orient itself to the Earth's North Pole. So that little needle on the leaf will slowly orient, if it's been magnetized, will slowly orient itself to Earth's North Pole. So for a long time, that was the only way we used magnets. Then a Danish scientist named Hans Christian Ørsted discovered the electromagnet. And an electromagnet is also a magnet, but it's not a permanent magnet, unlike the lodestone. It's a magnet that only exists when you turn on the electricity. So we're going to come back to that in the next slide. So how did Ørsted create a magnet out of a non-magnetic material? Well, he discovered that anytime you had current moving in a wire, it created a magnetic field, which will be known as the variable V later on in the next video. And this moving current, making this magnetic field in the wire, could actually deflect the needle of a nearby compass, a permanent magnet nearby. He also realized that the direction of the current ends up determining the direction that the magnet is deflected, so the direction of the magnetic force. There's a picture of him with his kind of original well, not a real picture of him, an artistic rendition of him, I assume, with his original electromagnet. And here is kind of a picture of what the experiment essentially looked like. It was just a wire connected to a battery, so a short circuit, essentially, a very, very high amount of current. And when the switch was connected, the magnetic compass needle that just happened to be on his desk, he was not setting out to discover anything about magnetism. He was actually playing with current. But he happened to have a compass on his desk and noticed that it deflected one way when the current flew through the circuit one way and deflected the other way when it went the other direction. So it was a pretty interesting discovery, given that up to that moment, no one had any clue that magnetism and electricity were related at all. So in the years since this discovery, we've really sort of honed in on what really magnetism is. And at the heart of it, all magnets are caused by moving charges. You have to have both of those components. So in our last unit, we had charges, but they weren't always moving, right? Whenever they're moving, though, then we're going to create a magnet. Of course, current moving in a wire, by definition, is a moving charge. And so that means every single time we flow current through a wire, we are creating an electromagnet, whether or not we noticed that in the last unit. So this is just a diagram of current flowing through a wire, and those little red arrows, loops, are representing the magnetic field that is created by the current going through that wire. Another way we can create magnetic fields is just by having quote-unquote free electrons or protons that are moving through space. When we have like lightning or even just charged dust particles, sometimes we send a beam of these electrons or ions through space and we use them to do things. One example is known as a cathode ray tube, which was our old television sets. Used to work by sending beams of electrons from one side to the other and using magnets to kind of deflect or move those things because they were magnets because they were moving. Therefore, we can use a permanent magnet to push and pull those free charges around as well. But it turns out that bound electrons, which are the electrons inside an atom, are also always moving. Electrons have a property known as spin, which means that they're orbiting around the nucleus, but the electrons themselves are actually spinning, and that creates a permanent magnetic field around every single electron. And so when we talk about permanent magnets, right, the magnet that we pull off our refrigerator, it's not easy to see where the moving electrons are in this. It's not like a circuit where you're clearly using a battery to throw those electrons through, but where the electrons are moving is in the spin of the individual atoms inside this electromagnet, or inside this permanent magnet. A note about this, that every electron that's spinning creates a quote-unquote dipole, which is a two-sided magnet that has a north and a south. So the single electron itself makes a two-sided magnet, and since we can't divide electrons in half, we can never create a one-sided magnet. So when I asked you a few slides ago why you'd never seen one, or if you'd ever seen one, the answer is no. There is no magnet without a north and south pole, because the very tiniest magnet, which is a single electron, still has both. So this is one difference between magnetism and electrostatics. We can separate positive and negative charges. We can have just a positive charged object or just negative. We cannot have just a north pole object or just a south, because at its heart it's made up of electrons. And that means that there is no such thing as a magnetic monopole. The word monopole is used to describe a theoretical one-sided magnet, and quacky scientists have claimed to find these for years, but as far as we know, they don't exist. So there's the picture of the electron showing how it itself, by spinning, creates a two-sided dipole magnet. So hopefully you're asking yourself, how do we turn these spinning electrons into a permanent magnet? And maybe more to the point, if all materials, every material, including this pen, has spinning electrons, why isn't every material a magnet? Well, if you put two magnets pointing in opposite directions near each other, so if this is north and this is south, and I take this magnet and I flip it so that this is north and this is south, the magnetic fields of these objects can effectively cancel out, which means that while every electron in every material everywhere is a magnet, most materials end up having no net magnetic field because the electron spins are all canceling out. In that diagram I just put up in A, it demonstrates, what happens if you just have a single spinning electron, you create a magnetic field. If you have two, they pretty much cancel out. They certainly cancel out in one direction. We still have a little bit of net magnetic field sideways, but if I get many of these electrons that are all spinning in different directions, then we're canceling out magnetic field in every direction in 3 dimensions, and we're left with no net magnetic field. And that's true for most materials like these pens. If you've had chemistry, I think they teach this in regular chemistry, but any case, there's something known as the Pauli exclusion principle, which states that in each electron atomic orbital, there can be exactly 2 electrons, and those 2 electrons must be spinning in opposite directions, which means that in every full orbital, we have canceled out the magnetic field effectively. And so hopefully this is going to give you a hint about what kinds of materials we end up able to make permanent magnets about, and what kinds of materials never will become a permanent magnet based on their atomic structure. So we can classify all materials in this world, generally speaking, into three categories, magnetic categories. There are some materials that are called diamagnetic, some called paramagnetic, and some called ferromagnetic. So in the next slides, I'm going to kind of go through what do those definitions mean about the atomic structure and about the magnetism of different materials. Diamagnetic materials are materials like this pen that have zero net magnetism overall. The reason, of course, is because all of the orbitals in the atoms inside these materials are full, which means they have 2 electrons that are spinning in opposite directions, and therefore the magnetic field effectively cancels out. Most objects around you are diamagnetic, wood, plastic, etc. No matter how you try, you can't get a magnet to attract to them. And the net magnetic field from these atoms is also 0, so they're not going to attract anything else. There's a fun little random quantum mechanics voodoo fact, and this is one of those things where I started digging deeper and very quickly got out of my league in terms of physics, but feel free to dig in yourself if you want. Materials that are diamagnets actually repel external magnetic fields, so not only are they not attracted, but if you try to change the magnetic field near it, it actually repels. And for some reason, scientists around the world have used this property to levitate frogs. I don't know why everybody wants to levitate a frog, but when you look up diamagnetic materials or YouTube videos of it, you will inevitably find these pictures of these tiny levitating frogs. And they don't seem to be hurt by this experiment. They're just levitating in space. But in any case, there you go. I would love it if you guys would go take more physics and explain why we can levitate a frog just because it happens to have full electron orbitals. The next class of materials is known as paramagnetic materials, and these are materials that are weakly magnetic. These orbitals do have some unpaired electrons, which allows them to have, at an atomic level, some net magnetic field. Each atom in these materials is magnetic, but generally speaking, those atoms then are randomly distributed due to the fact that they're moving around a lot, or just random entropy, or the fact that there's weak atomic bonds that are holding them together, which means that they're distributed randomly. So in these materials, each atom is a magnet, but the material itself is still not a magnet, and because sigma B is still usually 0. This is true about many chemicals, certainly materials that are in a liquid gaseous state, right, because those materials have entropy and are moving around. And it's also true about non-iron-based solids such as copper. So copper is a metal that is paramagnetic or very weakly magnetic. You generally speaking cannot, it's not strong enough magnetism to attract a magnet to a piece of copper. However, if you bring a very strong magnetic field near to one of these paramagnetic materials, it may be able to temporarily align some of those electrons to turn it into a magnet. So like you may be able to attract copper. If you had a strong enough magnet, you could attract a little bit of it, or some of those other materials that were mentioned. This is kind of a diagram showing on the left the randomly distributed magnetic fields of those atoms. And if you throw a strong magnetic field near it, it might be able to push and pull enough of those things close enough into alignment that the material becomes weakly magnetic. And the last class of material is known as ferromagnetic materials, and these are the strong magnets. So these are materials that have a large number of orbitals that have unpaired electrons, because remember, even in any atom, the vast number of the orbitals are full. But depending on the atomic structure, you can end up with multiple partially full electrons, orbitals. Iron, for example, if you remember your orbital diagrams from iron, actually has 4 orbitals with unpaired electrons, and that's a good hint about why iron ends up being such a base of so many magnets. Cobalt, nickel, and some of the rare earth metals such as neodymium are other ferromagnetic materials. Ferro, of course, is the root for iron. Not all magnets are iron-based, but most of them are because it's the cheapest, easiest, best, strongest magnet that we can get our hands on. So the orbital geometry and or the fact that these things have strong crystalline structures, which means that once we set them up as magnets, they freeze in place and basically keep their orientation, allows for big chunks of atoms to influence each other and to have the same magnetic alignment. So the way you sort of create a magnet from scratch is you take one of these materials and usually you melt it or heat it to a point where things are fluid and they're able to move. And then what you do is you bring another strong magnet, maybe an electromagnet nearby, something strong, that basically, as these things are fluid, forces them to all line up in the same direction. And then if you cool it down or freeze it, then they are trapped in that orientation where everybody's spinning in the same direction, and the material itself will have an overall magnetic field once it cools. The more aligned these things are, the better the magnet is, right? So this thing on the left, that could be a hunk of iron. Well, no, actually, that's probably my paramagnetic material. The picture in the middle is like a random chunk of iron. Random chunks of iron themselves don't act like magnets. I could take two hunks of iron ore, they're not going to stick to each other naturally. And the reason is because the domains, which are represented by these kind of crystal chunks, those are each like a crystal of iron. While each domain is magnetic, they are randomly oriented relative to each other. So again, it cancels out. And then that third material is the same chunk of iron. If we heat it up and then expose it to a magnetic field, it can basically forcibly rotate those iron atoms until they're all facing the same direction. Then if we cool it down and freeze it again, then when we're done, we have a really strong permanent magnet. Okay, we've reached the end of this video, and really the essential question is, what is a magnet? So hopefully at this point you have a sense, and that age-old question that kids have been asking ever since they first stuck something on a fridge, you can have an answer for. Thanks for watching.